Hey everybody, pardon my very relaxed attire. I'm getting ready to go out and do some yard work, and I thought I would throw together or finalize a video before I did that. So I'm not dressed the way you would normally see me dressed in the classroom. At least I don't think I could get away with dressing like this. This is just a brief introduction. What I'm doing right now is just a brief introduction to a video that I created in the fall of 2020 for the ergonomics class. In this video, I go over the NIOSH lifting equation and how that tool can be used for ergonomic assessment. Now, during the video, there's going to be references to different reading assignments, practice problems. If you are an NSU student and you would like for me to send you those readings or the practice problems, let me know and I can do that. But if you're not interested in those practice problems, when I mention a practice problem or a reading assignment, just ignore that. Most of you are going to be here just to learn a little bit more about the NIOSH lifting equation and how it could be used. All right, enjoy the video. The particular tool we're talking about in this module is the NIOSH lifting equation, also referred to as the NIOSH Work Practices Lifting Guide. And this is, if you look at the title for NIOSH, that's what you're going to see, the NIOSH Work Practices Lifting Guide, but normally we just call it the NIOSH lifting equation. For additional information, and you're not required to look at this, it's 164 pages long, but in that 164 page manual there's much more information about the NIOSH lifting equation and how to use it. We're not going into a lot of detail. We're just looking at the very basics of the NIOSH lifting equation. One thing that may help you out in the future with regard to the NIOSH lifting equation, it usually shows up on the ASP exam and the CSP exam. It's very common to have an ASP or CSP problem that will test your general knowledge of the NIOSH lifting equation. You won't have to know all 164 pages of the manual, just your general knowledge. Basically, it'll be testing your awareness of the equation and how the equation can be used. Right, it was developed by NIOSH originally in 1981, then it was revised in 1991, and that's what we're talking about in this module is the revised lifting equation. Still, 1991 is what, 29 years ago? There hasn't been a major upgrade to it in 29 years, but this is the revised lifting equation that we're talking about. Now, NIOSH, again, you probably all heard this before many times, but NIOSH is the National Institute for Occupational Safety and Health. It's part of the Centers for Disease Control. It's a government agency that is primarily interested in conducting research, investigating work-related hazards, work-related safety, and health issues as well. From their research, they make some very useful recommendations on how we can achieve a safer workplace. I've always said that if forget OSHA, if we just followed what NIOSH told us to do in our workplaces, we're going to be in good shape. We're going to see a drastic reduction in injuries if we just followed NIOSH. Now, speaking of OSHA, NIOSH is not a law, but oftentimes OSHA will use the NIOSH recommendations as the basis for a general duty clause violation. Remember, when it comes to ergonomics and lifting limits, there are no OSHA regulations, but OSHA can refer to the NIOSH recommendations and issue a citation based upon those recommendations under the general duty clause, which we talked about earlier in the semester. Now, the Work Practices Lifting Guide, again, NIOSH, the original was 81. This is revised in 91, as I said. It's an equation to calculate the recommended loading for different work tasks. It is very limited and it doesn't have a broad application, as we'll see as we get into it. But this is the general goal of the NIOSH lifting equation, is to identify a recommended weight limit, a lifting limit for different tasks. Along with this is the lifting index, which we'll also talk about. It's tied closely to the recommended weight limit. The lifting index is an estimate, or gives us an estimate of the amount of stress placed on the worker's body. And based upon the lifting index number, there are recommendations on how an employer should proceed. Should they modify a task? Should they completely eliminate a certain task and start all over again? But it will provide, this lifting index estimate will provide guidance on what we can do in the workplace. Talking a little bit more about the lifting equation, it's only for two-handed manual lifting tasks. The work surfaces, the floor, the ground where you're working, is assumed to be optimal. It's not slippery. It has a coefficient of friction of 0.4 or greater, which is a good coefficient of friction. That's going to be a floor that's not real slippery. And as a sidebar, to measure the coefficient of friction, there's an instrument called a slip meter. May have mentioned it before in previous units. But the slip meter can be used on a floor surface to measure the coefficient of friction. Now, it doesn't work on dirt or gravel outdoor work environments, but it does work when there's a smooth floor, concrete floor, a tile floor, a wood floor. It does work in those types of environments. Also assumes optimal temperature and humidity, which is very, very narrow range, 66 to 79 degrees Fahrenheit for the temperature and 35 to 50% humidity, which in the summertime in Oklahoma for an outdoor task, or let's say we have an unair-conditioned warehouse in Oklahoma in the summertime, those aren't optimal temperature and humidity conditions. Now, if it was an air-conditioned environment, that'd be different. But outdoor or in unair conditioned environments, this is rarely going to be applicable in Oklahoma or anywhere that experiences hot summers with high humidity. It would be relegated just for indoor air conditioned operations in the hotter part of the country, hotter regions of the world. And some other limitations. I said earlier it's really limited as far as its applicability. Here are some other limitations. If you pick up something and carry it, it doesn't apply. 2 steps is the maximum for which this equation applies. It's not for single arm lifts. It's not for any lifting that's done from a seated or kneeling position. If it's an unstable load, a container of liquid that sloshes around, making it unstable, doesn't apply to that either. It's not for wheelbarrows or shovels or any other tools that may have a loading as well. Not for high-speed lifting. Now, for these types of tasks that are not covered by the NIOSH lifting guide, the lifting equation, additional analysis is required. If I'm the safety manager and I'm doing an ergonomics assessment on tasks that have any of these limitations, I'm not even going to think about the NIOSH lifting equation. It's not useful. I'm going to go to other resources. I'm going to look at the Snook tables. I'm going to look at the ACGIH TLV for lifting. I'm going to ensure that my workers have good training. They're using good lifting technique. I'm going to try to minimize the load weight that they're handling. And NIOSH equation's not going to be useful in a lot of situations. But it is important to know this. Safety professionals have this awareness. They know about these different tools. Whether they ever use them or not, that's another issue. But you do, as a safety professional with a degree in EHS, this is something you need to know, and you will see it on certification exams. And as I've already said, it's used for calculating the recommended weight limit and the lifting index. And there it is again, used to calculate the recommended weight limit. Now the equation, now we're going to start talking about the equation. On the surface, it looks really simple, and it's not hard mathematically. There are only 6 variables and a load constant, which we'll talk more about. There are versions of the equation for metric measurements in kilograms and imperial measurements in pounds. We will only be talking about the imperial, since in the United States we still use pounds and ounces. As you prepare in the future for ASP, CSP type exams, you'll want to become familiar with both of the equations. They're the same equations, just some of the numbers are changed around. Now I will go ahead and mention now about the load constant. The load constant in metric is 23 kilograms. In imperial, it's 51 pounds, and that's what we'll be working off of, is that 51 pound load constant. And here's the basic formula. You have numbers for all of these different variables, and once you have the numbers for all those different variables, you multiply them all together. The complexity has to do with coming up with the numbers for each of these variables. Each of these variables, except for the load constant, requires some calculation, or you have to refer to a separate table. And we're going to see all of that. Now the math of it is easy. The math part of it is easy. Again, we've got in the load constant and these 6 other variables. Let's talk about those other variables. Again, load constant, horizontal multiplier. 10 divided by h. That's what you have to calculate to get the horizontal multiplier. H is the distance of the hands from a midpoint between the ankles. It's the distance, think of it as a distance out in front of the body. How far are your hands from the body is h. Then you have a vertical multiplier. The number that you have to plug into this equation here, or this formula here, is the distance of hands above the standing surface. That's when you're starting the lift. Then once you have the distance your hands are positioned at the start of the lift, you plug that distance into this formula. And then you come up, you calculate the vertical multiplier. Bear with me. I know your head's already falling off. You're already freaking out. Bear with me. This will all make sense, or more sense, once we start putting it into a problem, putting it into practice. Then we have the distance multiplier. This is the absolute value of the difference between the vertical height at the start of the lift and the end of the lift, or where you're placing the load, where the lift stops. If the lift starts at 20 inches and ends at 40 inches, D equals 20. And once we have D, the value for D, we plug that into this term. Asymmetry multiplier has to do with the angle of asymmetry relative to the sagittal plane. And the sagittal plane is an imaginary line drawn through the body, and it divides the body into left and right halves. That's the sagittal plane. If we are turned to the left, our asymmetry, or A, that angle, is not going to be 0. We want that angle to be 0. 0 means there's no twist. If we're turned all the way over around our hips, it's going to be 45 degrees. But ideally, our A value, or the angle, is going to be 0. Once you have that angle, then you plug that into this term to calculate the asymmetry multiplier. Now the frequency multiplier, that value is from a table, and we'll take a closer look at that table and how to use it. The coupling multiplier, that has to do with the quality of the grip, how well the worker's able to grip the object they're lifting. That is also taken from a table, which we will look at. Now let's put all this into the formula that we've gone over so far. This is the basic formula. Load constant times a horizontal multiplier times a vertical multiplier times the distance multiplier times the asymmetry multiplier times the frequency multiplier and times the coupling multiplier. A lot of multipliers there. But now let's take this basic formula and put it in the extended form. Okay, this is the extended form. Again, here's our horizontal multiplier. Here, well, let's start with the load constant. Here's our load constant. Here's our horizontal multiplier. Here's our vertical multiplier. And our distance multiplier. A symmetry multiplier. Then our frequency multiplier. There's no calculations. We just have to look it up from a table using the information that we're given. Same thing with the coupling multiplier. All right. Let's go ahead and look at another tool that can help us if we are using the NIOSH lifting equation, a task analysis worksheet. This is going to be used to record the measurements needed for calculating the recommended weight limit. Now, there are a lot of different forms of this worksheet. Whatever works best for you is fine. For our practice problem, I recommend that you use this particular worksheet. And this is the worksheet that I'm going to use as I go through a sample problem. Here is the frequency multiplier table that we'll use. And here is the coupling multiplier table that we will use. Based upon information about the lift, about the task, we will identify a coupling multiplier and a frequency multiplier coefficient. Okay, let's go ahead and do this. This hopefully will make sense to you if it's not already. Okay, in this situation, we have a worker that's lifting a roll of paper that weighs 44 pounds. The task is performed once each 8-hour shift and takes less than 1 hour to complete. The roll must be lifted off the floor using a grip point that is 15 inches above the floor. The load is placed on a shelf at a height of 63 inches. During the lift, the worker must step forward toward the press, and his horizontal hand position is 18 inches at the origin and at the destination. His hand position stays at 18 inches. There's no twisting that's involved. He's able to maintain good symmetry. There's no asymmetric angle, so no twisting is required. The worker's grip on the roll can be classified as fair. What is the recommended weight limit for this task? Okay. Let's pull up our worksheet and start filling in these numbers. First of all, hand location at the origin. Hand location at the origin is going to be 18 inches. And hand location at the destination, and the hand position doesn't change. So it's going to be 18 inches and 18 inches. Now we want to find the hand position at the start of the lift. Remember, the roll is on the floor and the grip point is 15 inches above the floor. So that's going to give us our hand position, our vertical hand position at the start of the lift. 15 goes there. Now we need the vertical position when we set down the load, where we're placing the load. I've already got this underlined, but let me underline it again. It's going to be 63 inches. Whoops. 63 inches. So we plug that in. Now, once we have the 63 inches and the 15 inches, we can use that to calculate our vertical distance of 48 inches. And we'll use that in the formula. Okay. Asymmetry is easy on this one. There's zero asymmetry. He's not twisted either way. He's straight ahead, so that's a 0. Same thing at the destination. There's no need for twisting any time during this task. Now we want to look at the duration, less than 1 hour. And again, that's in our task description. Takes less than 1 hour to complete. And we will use this when we identify the multiplier for frequency, the frequency multiplier in the table. So that's everything we need so far. Oh, I do want to make a point about the vertical distance. I have it up here on the screen. The vertical distance is the absolute value. If we subtract the destination from the origin position, it's, again, we've got the start or origin there at 15 and the stop or end at 63. 15 minus 3 is negative 48, but we're using the absolute value, so ignore the sign. It's going to be 48 when we plug it into our formula. Okay, so we've got everything except the frequency rate and the frequency multiplier and the coupling multiplier. So let's look at the frequency multiplier. And here's the table we use. Our work duration is less than 1 hour, and our frequency is once every 8 hours, which is less than once per 5 minutes. And duration less than 1 hour, and we're only making the lift once per 8-hour shift. So the frequency is less than 1 lift every 5 minutes. And it says down here, for lifting frequency, for lifting less frequently than once per 5 minutes, set F to 0.2. Now 0.2 is not what we plug in here. We use the 0.2 in this table. We use the 0.2 in this table along with our work duration less than 1 hour to find what our multiplier should be. And there's the row for our frequency. Here's our column for less than 1 hour total duration of the task. And where these two rows intersect, that is our frequency multiplier. And it's going to be 1.0. That's what we're going to use in our formula, is 1. Now, one thing that doesn't apply here, it only applies in certain task situations, but also the vertical height or the vertical position of your hands. If it's less than 30 or greater than or equal to 30, then that has to be considered as well. It doesn't apply in this situation. And if you excuse me, if you look through the table, there are very few situations where the height of the hands actually changes the frequency multiplier. Not until you get down to 13 lifts per minute. At that rate does it start to apply. All right, let's talk about the coupling multiplier. Again, if you look at our table, we've got everything but the coupling multiplier. We qualitatively identify our coupling as fair. And this is based on the fact that we don't have any handles, but the worker is able to grip the roll of paper at each end. And he can grip the opening in the roll. He can put his fingers in the roll, which gives him a not good, but a fair grip. Based upon that qualitative determination of the grip quality and also the starting height of the lift, we can find the coefficient that we'll use as our coupling multiplier. Okay, fair, there's the row for fair. There's the column for hand position less than 30 inches. Again, our hand position at the start was 15 inches. So our coupling multiplier that we're going to use in our calculations is 0.95. Okay, now we have everything that we need to do the calculations. And that's what we're going to do on the next slide. And here's our summary table, our task worksheet with all the information we need. Here's our basic formula. And here's the extended formula that we'll actually plug these numbers into. Now, before I start plugging in numbers, let me mention the existence of online calculators. There are online calculators that you can find on the internet that's supposed to do this NIOSH lifting equation. I found a couple of them that are accurate, but they're a pain in the rear to use. They're not worth the time and effort. Those are the free calculators. Now, if your company needed to use this equation a lot and they were willing to pay a fee for better software, for a better app, there are apps that are very good to do these calculations, but they're not free. You have to pay for them. The ones that are free, I don't recommend using them. You can try them when you do the practice problem if you want to, but I don't recommend using them. The NIOSH even has an app that you can put on your iPhone or your Android phone, your Samsung, whatever Android phone you have. And there have been a lot of complaints about the app not being accurate, not being easy to use. If you need to do this for this class, just go ahead and calculate it out for the practice problem. That's my recommendation to you. All right, we've got our basic formula, our extended formula. Everywhere we see letters, we're going to plug in a number for those letters. We're going to plug in a number for LC, that's our load constant. We're going to plug in a number for H. We're going to plug in a number for V and D and A, F, M, and CM. And all these numbers are up here on our task worksheet. So here are the numbers that we need to plug in for the intermediate calculations. For horizontal multiplier, which is 10 divided by H, H is 18. That's, again, horizontal distance of the hands from the body, 18 inches. For our distance multiplier, we need to plug in the vertical position of our hands at the start of the lift, which is 15 inches. Now 30 is a constant. 30 stays the same. Yeah, any of these numbers in the extended formula, any of these numbers up here, those are constants. The only numbers that you have to insert are the ones that we're going to be inserting. And then for the distance multiplier, we have the distance, which is the difference between the start and end of the lift. 63 minus 15 is 48. So we plug that in. Our asymmetry is 0. Plug that in. Our frequency multiplier is 1. Our coupling multiplier is 0.95. Again, mathematically, all this is addition, subtraction, multiplication, and division. It's not anything, there's no square roots, there's no logarithms that you might see with some other industrial hygiene type calculations. It's just plug in the numbers, make sure you got the right numbers, plug in the right numbers, and then do the addition, subtraction, multiplication, and division. And that's what we're going to do in the next iteration of the formula. We're going to do a couple. I should have went ahead and done this one, but we'll get to it later. The 15 minus 30 is 15. 1.8 divided by 48 is 0.375. 0 times 0.0032 is 0. Then we just pull down our frequency and coupling multipliers. And now if I was doing this for real, I probably wouldn't go in as much detail as I'm going with all the different iterations of the formula, but I don't want you to get lost. I want you to see where all the numbers are coming from. Coming down to the next level. Okay, here we've got 10 divided by 18, which is 56 for our horizontal multiplier. For our vertical multiplier, we've got 15 times 0.0075. No change here, no change here, no change here. Next iteration. I'm having some technical difficulties. Oh, here we go. All right. No change for the horizontal multiplier. Vertical multiplier 1 minus 0.1125, 0.8875, 0.82 plus 0.0375, 0.8575, 1 minus 0 is 1. Then no changes for the frequency or coupling multipliers. Now let's go ahead and round everything to 2 decimal places. At this point, now this particular value here I already rounded. The horizontal multiplier already rounded it to 2 decimal places. But let's round the vertical multiplier to 0.89, the distance multiplier to 0.86, everything else is the same. Now all we got to do is multiply all these together. And let me go ahead and bring up the calculator. And we'll do the multiplication real quick. We got 51, our load constant, times 0.56 times 0.89 times 0.86 times 1 times 1 times 0.95 is 20.766. We're going to round that to 20.77 pounds is our recommended weight limit. And now one thing you're probably thinking when I was doing this multiplication, why is he doing that? You really don't have to multiply times 1 every time. I went ahead and multiplied everything, so not to lose any of you, but I really didn't have to do the multiplication by 1 anywhere in this, because 1 times any number is going to be the number that we multiplied 1 by. So, and now we've got the recommended weight limit for workers lifting these rolls of material. But our problem is, hey, the roll weighs 44 pounds, but NIOSH lifting equation says it shouldn't be more than 20.77 pounds. So what do we do as a safety manager, as an ergonomist? Well, that's where the lifting index comes in. The lifting index is the ratio of the load weight to the recommended weight limit. It's an indicator of the magnitude of stress on the worker's body. It's a simple calculation. The lifting index is the weight of the object divided by the recommended weight limit. In our problem, the 44-pound object is heavier than the recommended weight limit. The lifting index, again, we plug in 44 for the object, 20.77 for the recommended weight. We come up with a lifting index of 2.11. But what does that mean? Well, NIOSH gives us some guidance on how to use the lifting index. If it's 1 or less, if our lifting index is 1 or less, that's ideal. It's excellent. Injury is not likely unless something out of the ordinary occurs. But if it's 1 or less, we're good. If it's greater than 1 but less than 3, there is a risk of injury and modifications are recommended. If it's 3 or greater, high risk of injury, modifications required. Again, this is coming from the NIOSH recommendations. If you go back and look at that 164-page guide, you're going to find these suggestions for interpreting the lifting index. If I was the safety manager in this situation, I mean, the rolls, we may have the option of using smaller rolls that were lighter. If that wasn't an option, I'm going to look for other modifications that we might be able to use. Maybe there's some type of a lift table that we could use to lift the weight up to the shelf height where it needs to go. But for sure, I'm going to make sure that the guys I'm working with, the women I'm working with, are using proper lifting technique and aren't getting in a hurry as they make the lift. I'm also going to recommend, even though it's only 44 pounds, I'm also going to recommend team lifting, 2 people teaming up on it. I think really most importantly, good lifting technique, also stretch and flex. Stretch and warm up before you make the lift. Okay, now this was a very simple situation, very simple task. Now, what you might run into are more complex tasks where you have to calculate multiple recommended weight limits. You have to calculate a weight limit for the beginning of the task and a different weight limit for the finish of the lift or the finish of the task. The document that I mentioned earlier, it will have all that kind of additional information for more complex task situations. An example of a situation where you would want to calculate the lift at the origin, where you might have a different recommended weight limit at the origin and a different recommended weight limit at the destination, would be during the installation of a transmission in an automobile. That transmission has to be lifted and placed precisely under control, so all of the bolt holes will line up and you can secure the transmission to the bell housing, transmission to the engine. In that situation, you need to calculate the recommended weight limit at the origin and at the destination. So you'd have two recommended weight limits. One good thing about putting a transmission in a vehicle, they have jacks designed for that purpose. You jack it up into position, all the weight is on the jack, and you can perfectly position with very little exertion. And that's always look for tools, equipment that can help us with the heavier loads. All right. If you have any questions, go back and watch the video. If you still have questions, call me, text me, email me, get a hold of me, and I'll see if I can help you. What I would like for you to do now is to consider the task on the screen right here. This is going to be your practice problem. After you complete the practice problem, which includes filling out the worksheet. Now here's the worksheet. You'll have it available on Blackboard. Here's the worksheet. Fill out, get all your numbers in place. Then you do the calculation using the formula that we have here. Then after you've done that, to receive credit for doing the practice problem, complete the lifting equation quiz. It'll probably be 4 or 5 questions based upon this problem. For sure, I'm going to ask you what the recommended weight limit is and what the lifting index is. And there may be other questions based upon some of these numbers. I might even ask you what's the horizontal multiplier coefficient? What is the frequency multiplier coefficient? So, all right, well, that's it for this module. Have any questions, let me know. I'm here to help. Happy to help. Just give me a call.